In this video, we'll be covering section 12.1, sequences. We have 4 objectives. We will write the first several terms given a sequence. We will write the terms of a sequence defined by a recursive formula. We will introduce summation notation, and then we will finish by finding the sum of a sequence. So our definition of a sequence is going to be a function whose domain is just the set of positive integers. We might want to think of a sequence as just an ordered list of numbers, but the definition that we've given here is going to be more useful to us. So an example of a sequence that you might see would just be a list of numbers, something like this here: 1, 1/2, 1/3, 1/4, and it just goes on and on. But the list of numbers has a specific order to it. In other words, we say this is the first element, this is the second, the third. And so what we're really doing there is we're forming a mapping. We are mapping the essentially the natural numbers to this set of numbers down here. So that's why we're saying we can think of it as a function whose domain, the input, is just the set of positive integers. So the formula that actually generates this specific sequence is the function 1 over x. So prior to talking about sequences, when we were studying this type of function, the graph of that function would have been a nice, smooth, continuous curve, because the domain was, in this particular graph, was just all positive numbers. So what we're saying now, if we want to study this as a sequence, we're going to restrict down to just plugging in the positive integers. And so then the graph of this is not a nice smooth curve, it's a set of discrete points. So this would be the way we would understand it as a sequence. You can see the range elements are just the numbers that we have listed over here. Now, instead of using function notation, we are typically going to use a sequence notation, and the way we do that is usually just with a lowercase letter, and then we use a subscript to denote the domain element. So in other words, a sub 1 just means the first term. It means plug 1 into the function that generates the sequence. A sub 2 is the second element, a sub 3 is the third, etc. And so if I write a sub n, this just represents the nth element of the sequence. In other words, it's what you get when you plug n into the generating function, which for this particular example would be 1 over n. So most of the time we're going to be writing them using this notation, but you can keep, in your mind, you can think there is actually a function defining the sequence in the background. So let's look at our first example. So our textbook likes to represent the function or the sequence as a set of numbers, so you'll typically see braces here, but most textbooks would just write this as a sub n equals n minus 1 over n. They represent the same thing. This is the function that generates our sequence. It says we're going to write down the first 6 terms and then we're going to graph them. So a sub 1, the first term, is found by just plugging 1 in. 1 minus 1 over 1, well, that's 0 over 1, which is 0. So this corresponds to the point 1, 0. The first term, its value is 0. So that's where you can see this point is coming from. Moving on, a sub 2, the second element, would be 2 minus 1 over 2, or 1/2. A sub 3 would be 3 minus 1 over 3, which is 2/3. Now at this point you can see a pattern emerging here, and that pattern is that each one of these is a fraction where the numerator is 1 less than the denominator, and the denominator is always matching the place in the sequence. So I don't have to keep plugging into this to generate them. I could go straight to the answer. I know the denominator is 4 and the numerator is 1 less. So a sub 5, denominator is going to be 5 and the numerator is 1 less. And then finally the 6th term would be 5 over 6. And that is exactly what this expression really should be interpreted as. It's a fraction where the numerator is 1 less than the denominator, which you can see is exactly what we see here. So oftentimes, like I said, this could be represented as a set, so I'm not actually sure how they're going to have you entering it in Math Excel. This would be another way to kind of represent the sequence. It's a set, an ordered set of numbers, but it's infinite here. It goes on forever. Okay, so I've graphed a few more terms of this sequence out to 40 terms, and this sequence has an interesting property, and that is that it converges to a number. If I were to draw in the line y equal 1, you can see that the output of this sequence is approaching that line. So where this ends up going in calculus is you start using what's called a limit. And we take the limit as n goes to infinity. Not every sequence will have a limit, but this particular one does. As you make n larger and larger for the values of this sequence, it approaches 1. So the limit of this sequence equals 1. Or we could actually just put in the actual generating expression as well. So n minus 1 over n. This limit is equal to 1. Now in calculus we'll actually need to do some work to prove why this is true, but this is where this is heading in the next course. Okay, let's try another one of these. So this one's a little bit more complicated. Let's start with the first term. We're going to have negative 1 raised to the 1 plus 1, so that's going to be squared, multiplied by 2 over 1. If we take negative 1 and we square it, that's going to wipe the negative out, so this really doesn't contribute anything. You just get the value of 2. Alright, second term is going to be negative 1 to the 2 plus 1, which is cubed. And then the fraction is just going to be 2 over 2. Now, this negative is raised to an odd power, which means it is still going to be negative, and then 2 over 2 is just 1. Third term, negative 1 to the 4th power multiplied by 2/3. Right? We just plug the index place in the sequence into the denominator there. So again, negative 1 raised to an even number, that's going to wipe it out just like it did for that first case, so we're just going to get the 2/3. Then fourth term is going to be negative 1 to the 5th power multiplied by 2/4. So again, we have a negative raised to an odd power just like this case here, which means it is going to come out negative, and then we just need to reduce this so we get negative 1/2. Okay, so let's look at the pattern that's emerging here. So what we see is that the sequence changes from positive to negative, and just keeps going back and forth. So we call that an alternating sequence. Anytime you see this expression in front of a sequence, it's going to be alternating. Whether it's negative 1 to just n or negative 1 to n plus 1, anytime you have negative 1 raised to a power that has the index for the sequence on it, then it is going to alternate from positive to negative. Now the other thing that we can see is that the actual fraction is always going to have the index as the denominator and 2 as the numerator. So we don't have to keep plugging everything into this. We can see that anytime it's an odd index, it's going to come out as positive. So I know this is positive. I know the denominator is 5 and the numerator is 2. And then for the sixth one, it's an even index, so for this particular sequence, that's always going to come out negative, and then it'll be 2 over 6. That one could be reduced to negative 1/3. So now we just need to plot each of these. So the first one corresponds to the point 1, 2. Next one is the point 2, negative 1. Then 3, 2/3, etc. Okay, let's go ahead and plot these points then. Alright, some of these are just a rough approximation, but you get something that looks kind of like this. Okay, let's look at the graph with a few more points put in there. So again, I've graphed 40 points, and once again, you see that the values of this sequence seem to be converging again. So again, we could say that this sequence has a limit. If we take the limit of negative 1 raised to the n plus 1 multiplied by 2 over n as n approaches infinity, it looks like the values, the y values in this case for this sequence, get closer and closer to 0. Turns out that they never actually equal 0, but the point is that you can make this expression as close to 0 as you like by just choosing larger and larger values of n. You can also see the alternating part of the sequence. It goes positive, negative, positive, negative, positive, negative, and just keeps oscillating back and forth between those, but they are getting closer and closer to 0 the further you go out. Alright, let's try one more. So this one is defined as a piecewise function. We have a certain definition if the input is even, and a different definition if the input is odd. So let's start with the first term, c sub 1. That's an odd index, so that means we need to do 1 over 1, which is 1. C2, the second term, well, 2 is even, so we don't do anything. We just get 2 out. C3, that one's odd, so we're going to do this definition, 1/3. C4, even input again, so we just get that number back. C5 is going to be 1/5. And then C6, again, just that's an even index, so it just comes out the same. So there are the inputs. The corresponding points would be 1, 1, 2, 2, 3, 1/3, etc. Okay, then we're going to take these points and we're going to graph them. Okay, so there we have a rough approximation for the graph of these points here. Again, let's look at the graph with quite a few more points put in. Now, in order to get this to fit, I had to stretch the y-axis out, and what that ends up doing is it makes it look like all of these points down here are actually on the axis itself, but they're not. They're actually slightly above, but they're getting closer and closer to the x-axis. So for this one, this is our first example of a sequence that diverges. It does not converge to a single number. Every even is just increasing. It just keeps going up. These are all headed towards infinity. But the very next number is going to give you an odd number, and those are all converging down to 0. So for a sequence to have a limit, all the values have to converge to one single thing, and these are not doing that. There's part of them are moving up here towards infinity, and part of them are moving closer and closer to 0. So for this one, the limit of c of n as n goes to infinity, we would say it does not exist. This is a divergent sequence. Okay, so like I said, a lot of times a sequence is just given as a list of numbers, and so what we want to do is come up with a formula, a rule, for the general term of the sequence. In other words, if this sequence is defined by a, we want a formula for a sub n. So this really just comes down to looking for a pattern. How is each of these formed? Well, notice that each one of them has a denominator, and the denominator matches the exponent. Even this first term, the first term on this one, could be written as e to the first over 1. So the thing that's increasing, that typically is going to represent your n. So a sub n, every term has an e, they're all raised to the nth power, and then we also divide it by n. So that would match this sequence. If you plug 1 in for n, you get the first term, plug in 2 for n, you get the second, plug in 3, etc. This works to generate all of the terms in that sequence. Okay, let's try another one. So the next one, again, we have fractions here, but the denominators are not just increasing by 1. So we want to look for some pattern amongst these numbers here. And you might say, oh, they're all multiples of 3. That's good, but what a lot of people are tempted to do is they say, okay, it's going to be 1 over 3n. So when you're doing these, what you want to do is test it. Does this actually work? If I did a1, well, the very first term would be 1/3. That doesn't seem to work. Okay, so 1 over 3n didn't work, so let's go back and look at these a little bit closer. Notice that each of these numbers they're multiples of 3, but more importantly, they're powers of 3. And now you see an index here that is increasing by 1 each time. So we could try to just do 1 over 3 to the n. But again, we should test this. So a sub 1, according to this rule, would be 1 over 3 to the first. It'd be 1/3 again. And again, that's not working for us. So let's try to modify this. In a sense, we need to shift everything back by 1, or we need to think of this one also needs to have a power of 3 in the bottom, and that power would have to be 0. So to get that to happen, we could do 1 over 3 to the n minus 1. So that way, when we plug in the first term, it'll be 1 over 3 to the 0, which is 1 over 1, which is just equal to 1. And then if we tried the other ones, a2 would be 1 over 3 to the 2 minus 1, which is going to be just 1/3. So now it matches, now it works. So this is the general term that generates that sequence. Okay, so next one. we've got 1, 3, 5, 7. What I notice here is every single time it's going up by 2. It's adding 2 each time. So if we try to use that fact that we're adding 2 each time, this is what a lot of people are tempted to do. They say, well, maybe it's n plus 2. We're adding 2 each time to get the next term. But again, let's test this. A1 here, if I plug 1 into this, I would get 1 plus 2, which is 3. That doesn't match that first term. If I try the second one, A2, that would be 2 plus 2, which is 4. Well, this sequence is not even going up by 2. It's actually only going up by 1 each time. So this is not the correct way to handle this. We'll see more why when we actually get to the next section. Okay, so a different way to think about this is these are all odd numbers. So what's the definition of an odd number? Well, an odd number is a number that's not even. What's an even number? Even numbers are multiples of 2. So if we take a multiple of 2 and then we simply increase by 1, that's going to be an odd number. This will generate odd numbers, but let's see if it generates the ones that we want. So A1 would be 2 times 1 plus 1. That comes out as 3. That's not what we want, but let's do one more. A2 would be 2 times 2 plus 1. That's 5. Notice these are numbers that we want, but they're shifted over. So to fix this, all we need to do is start off by subtracting 1 rather than adding 1. Now let's test it. A1 equals 2 times 1 minus 1. Well, that's going to be 1. Bingo, we got that. A sub 2 is 2 times 2 minus 1. That's 4 minus 1, which is 3. That one works. A3 would be 2 times 3 minus 1. That's 6 minus 1, which is 5. So it looks like we have it there. This is going to work. When you see the fact that we are adding 2 to move through this sequence, where that 2 actually comes from is this right here. And it's confusing because you look at it and say, well, that's multiplication, but this says that we're adding. And we'll see in the next section when we get to this sequence is called an arithmetic sequence, and we'll see why that actually turns into multiplication here. Okay, next one. This is one, for some reason, this is the one that usually throws people off. When people look at this sequence, they have a hard time seeing what the pattern is. They first look and see, okay, well, what's being added? On the first one, we added 3. On the next one, we added 5. And then we added 7. And then we added 9. So we're adding odd numbers. But it's not clear how to handle that. Well, there should be something else that jumps out at you. Something about these specific numbers. And that is that the first one could be written as 1 squared. Second one is 2 squared, then 3 squared, then 4 squared, 5 squared. These are all perfect squares. And that's how we're going to get the formula for it. So a sub n is just n squared. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So those are all just perfect squares. Okay, let's try another one. All right, so first thing to notice here is we have an alternating sequence. Positive, negative, positive, negative. So when you have an alternating sequence, we know it's always going to start with -1 raised to some power. Now we need the first one to come out positive. So I can't just do an n here, because if you plugged 1 into this, that's going to give you a negative on your first term. So I've got to shift it over by 1. I could do n plus 1, or I could actually do n minus 1. Either one will work. But now when I plug in the first number, I'm going to end up with a square as my exponent, which will cancel the negative. When I plug 2 in, I will have -1 cubed, which will give me the negative. Okay, so this will handle the alternating part. So now we just need to figure out the fractions. Well, we can see if I put the denominator on this, the numerators are all 1, and the denominators are just increasing by 1. So the fraction you're multiplying by is just 1 over n. So that will generate that sequence there. Okay, so a symbol that we are going to see show up in this chapter is the factorial notation. We should have talked about this last year, but if we didn't, when you see an exclamation point, that is a factorial, and the way it works, if we just look at the example for 5 factorial, it means take 5 and then multiply every positive integer down to 1. form the product of 5 times 4 times 3 times 2 times 1. That product is 120. So 5 factorial is 120. And that's how it works for any of them. So if I want 28 factorial, I start with 28, multiply by 27, multiply by 26, and just keep doing that until you get down to 2 times 1, and just form that entire product. So this is what a factorial is. In general, you would write it this way. N factorial would be start with n, multiply it by the integer that's 1 less than that, which is n minus 1, then times n minus 2, times n minus 3, all the way down until you get down to 1. Now we define just as a convention that 0 factorial is 1. And then also 1 factorial is defined to be 1. Now, one useful fact for factorials is, I think it makes most sense if we look at it down here. If we start with, let's say, 8 factorial. Well, 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And notice that this right here is also a factorial. That's 7 factorial. So 8 factorial could be thought of as 8 multiplied by 7 factorial. So that's all this is saying. You can do this with any type of factorial. If I want, 99 factorial, it's really equal to 99 times the previous factorial, which would be 98 factorial. This is helpful for simplifying these expressions at times. For these two particular examples, it's not that useful, but it does give us a formula that we can use in general. N factorial is the same as n times n minus 1 factorial. Now, factorials give us an example of what we call a recursion formula. What you just saw here is that we can define the next factorial in terms of the previous factorial. So let's try to make this idea of recursion a little bit more clear. Suppose I give you a sequence where I tell you that the first term is 5, and then I say to get the next term, I'm going to call that a sub n, you have to take previous term and add 3, let's say. So that's the rule for generating this sequence. Start with the first term being 5. To get the next term, take the previous term and add 3. So let's try generating this sequence. A sub 1 would be 5. A sub 2 says take the previous term, which is a1, and add 3. In other words, take 5 plus 3, you get 8. Third term. The rule says take the previous term, which is a2, add 3 to it. So a2 we found was 8, and we're going to add 3 to that. You get 11. And you can just keep this process going. So if we did keep it going, what would be the formula for a sub n? Well, it says take the previous term would be a sub n minus 1, and add 3 to that term. This right here is what we mean by previous term. A sub n minus 1 is the previous term. So this is a recursion formula. It generates the next term in terms of the previous term. So let's try an example of that. When you have a recursion formula, you always have to be given a starting value. Without a starting value, you can't generate the sequence. So we are given first value of this one. The first value is just 1. Now, according to the recursion formula, it says to get the next value, you take the index, whatever index you're on, and multiply it by the previous term. So in this particular case, we would take n, which is 2, it's the index, and multiply it by the previous term, which is s1, 2 times the previous term. So in this case, it's 2 times 1, which is just 2. All right, third term, take the index, which is 3, multiply it by the previous term, which is s2, and we just calculated s2 is 2. So 3 times 2 gives you 6. S4, take the index, which is 4, multiply it by the previous term, S3. We calculated S3 as 6. So 4 times 6 is 24. You can see it's going to start growing pretty fast here. Fifth term, take the index, multiply it by the previous term, multiply it by S4, which is 5 times 24, and that comes out to 120. So this is what we mean by a recursively defined sequence. All right, let's try another one. This is actually a very famous sequence. Now this one has two generators because the generating formula that we have here says to get the next term, you take the two previous terms. This is the one that came right before it, and this is one from 2 terms ago, and add those two together. So let's write this one out. So U1, the first one is 1. U2 was also 1. U3, according to this formula, is take the term 2 terms before, U1, and add U2. This is just saying add the 2 previous terms. These are the 2 previous terms. We're going to add those together. 1 plus 1 gives us 2. U4, it would say to do U2 plus U3. These two added together. So that is 1 plus 2, which is 3. All right, U5, we're going to stop using the U notation. The definition says add these two together. So it's 2 plus 3, which is 5. U6 is going to be these two added together, 3 plus 5, which is 8. I guess we went a little further than we had to. So the sequence that you see here, let's just write it out in a list form here. It was 1, 1, then it was 2, these two added together, then these two, 3, then 5, then 8, then 13, then 21, then 34, and just on and on like that. Each term is the sum of the 2 previous terms. So this sequence has a famous name, has its own name. It's Fibonacci. So hopefully you've heard that term before in either a science class or in a previous math class. So we'll see more with this sequence as we move forward. It's a very important one. It's used a lot in science. It's used to model population growth and shows up a lot in nature. Okay, the next thing we want to look at is adding up the terms of a sequence. So that is called a summation, or it is also a series. You could think of it as the sum of a sequence is a series, which we'll study more closely in the next section as well. So we want a convenient notation for representing the sum of a bunch of terms. And that's where summation notation comes in. What you see there, that funky looking, looks like an E, this is actually the Greek letter sigma. It's the capital version of the letter sigma. So it just represents sum. It means you're going to add up all of the terms a sub k, where k starts at 1 and increments, goes up by 1 and stops with n. So for example, if I said the sum of k, where k equals 1 up to 5. The idea is you're going to start with this k value, you're going to plug it into this expression, so we would just plug 1 into that, and then you increment it. Now k is equal to 2, plug 2 into that. Then plug 3 into it. Then plug 4 into it, and now we're up to the upper limit. 5 is the last thing that we plug into it. And then you could just add those together. This notation represents the exact same thing as this. Now you can get more complicated with this. So for example, we could come back and say, okay, I don't want just k here, I want k squared. Well, then each of these would end up being squared. Each individual addend would have a square on it, which would obviously then change the value of the sum. So you can get as a complicated expression as you want to put here. Now when using sigma notation, we will typically use the index of k. That will be the thing that we use to generate. But it's a dummy variable, so you can use anything as an index for a summation, meaning that you don't have to just use k, you could use n, you could use p, you could use any letter that you want. But for us, the most common letter is going to be k. Now we do have to be careful. You can't have n here and also up here. So you can't double dip like that. But as long as it's not as an upper limit of the sum, you could use the letter of n. All right, let's try a few of these. So all we're doing is writing out the sum. We're not going to evaluate them. We're just expanding the sum. So this first one says we're going to start by plugging 1 in for k, so it'll be 1 over 1, plus, now increment, k is now 2, it goes up by 1 each time, and then we just keep going. Now this says you're going to go up until you get to n. Well, I don't know how big n is, so we'll just use an ellipsis, and the last term would be 1 over n. You plug that in as your last term. And that's it. There's nothing else we can really do with that. Let's try another one. So now we're using factorials. So the first one would be 1 factorial, then 2 factorial, 3 factorial. We're just incrementing the k by 1. And again, we're going up to n. So we'll do the last two terms. So the second to the last term would be n minus 1 factorial. And then the very final term would just be n factorial. Again, we can't really simplify this. This is going to be a giant number, but we don't know how big n is to begin with. Okay, let's try going in the reverse direction. This is usually trickier. We want to write this in summation form. Now, one way to think about this is you could think of each of these individual addends as terms in a sequence. And what we need to do is figure out a formula, really in terms of k actually, an a sub k formula for that sequence of numbers. Now, what I notice is all of the numbers have a square on it. So we're definitely going to have a square in our generating formula. And if we look at the numbers in the base, it looks like they're just increasing by 1. So if they're just going up by 1, I would say these are all in the form k squared. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, up to 9 squared. So this is the generating thing that's going to be in our summation. We're doing the sum of k squared. The first value of k is equal to 1. And we're summing all the way up to the last value is 9. If you put 9 into this, you get that. All right, so that's a valid answer. Notice I did not say it is the answer, and that is because for this type of problem, there are actually infinitely many ways to write a solution, and it's what makes it trickier. So for example, let's just say that for some reason, I needed the index to start at 0. I have to plug 0 in first. For whatever reason, let's just say that's the requirement. I can't start with 1. Well, then what we would have to do is modify this generator here. What we would need is we would need to put k plus 1 so that when you plug 0 into this, you would actually get 1 squared there. So kind of just shifting it over. The other thing that's going to change is the upper limit. I can't put 9 here because if I put 9, this sum would end with 10 squared. Put a 9 here plus 1, you'd get 10 squared. So shifting down here also shifts the upper limit as well. It would have to stop. This one would have to go from 0 to 8, where this one goes from 1 to 9. These are both perfectly valid solutions. They both work. And you could take this as far as you like. So for example, I could say I'm going to do k minus 3. I'm going to start with k minus 3 on the bottom, or sorry, as the generator. Now I need this expression to, my first k value, when I plug it in, I need to get this to be 1. So what would k have to be? Well, it'd have to start with 4. If I plug 4 into this, then I'm going to get 1 squared. Then to figure out the upper limit, we would need to say, well, what k value do you plug into this so that you get 9 out? Well, it would go up to 12. K going from 4 to 12 will still generate the exact same thing as this. Now, do you need all of those? Absolutely not, but you need to understand there is going to be an infinite number of ways to write out that expression. Okay, let's try another one. Okay, so we see fractions, and we see that the denominators are not just going up by 1, but they're actually powers of 2. So we could think of this one as 2 to the 0, I should say. This is 2 to the first. This one is 2 to the second, 2 cubed. So the denominators are all just powers of 2. So we would have 1 over 2. If we tried to just do 2 to the n, then what we would have to do is we would have to start with, I'm sorry, let's use k. I'd have to start with k equaling 0. So then what would the upper limit need to be? It wouldn't just be n, because then the sum would stop with 1 over 2 to the n, and we're supposed to stop at n minus 1. So now if I plugged that in, that would give me this as the final term. So this is one valid answer, but maybe we want the index to start at 1, which is pretty common for us. Then the way that's going to shift is the exponent down here would need to be k minus 1. So that now you're plugging 1 in, and you get that 1 over 2 to the 0. The upper limit for this one would get to be just n this time, because now when you plug n into this, you do end with that term there. All right, so either one of those would be a valid answer. Okay, summations have lots and lots of properties, and these properties really just come from the normal algebraic properties that you already know. So these look really complicated, but they actually should kind of be common sense. So this first one here is saying if you have the sum of a constant times some sequence, the way to expand that is you'd have c times a1, c times a2, c times a3, all the way up to c times a sub n. Notice every one of these has a c on it, so you could factor the c out. That's just distributive property. What you're left with is the sum of these terms here. This part could be written back in summation form as you see here. So in effect, what happened is we got to take this out. You can just factor it out. So what this might look like in practice is if you have the sum of 3k, where k equals 1 up to, let's say, 12, here's a constant times some generating formula. This constant can come out. You are really applying the distributive property. You're just factoring out that 3 since it's common to every one of the terms. So that's all this first property is saying. The second property says if you have a summation and inside the summation you are adding the terms of a sequence together, then what you can do is essentially distribute the summation to each one of those. You might think this is actually the distributive property, but it's actually not. This is a combination of the commutative property and the associative property. If we were to write out the left-hand side of this, the sum of a sub k plus b sub k, where k equals 1 up to n, this would look like a1 plus b1 plus a2 plus b2, and you would just keep that going until you got up to the last term, which would be a sub n plus b sub n. Now all of this is addition, so we don't really need parentheses at all. So what we can do is just drop the parentheses and swap all the terms. Using the commutative property, we can just group all the a terms together, a1 plus a2 plus all the way up to a sub n. Using commutative property, just put all those at the front and then add up all the b terms, grouping all of them together. This could then be written in summation form as you see here, and then this one is obviously this one here. So this is really commutative and associative property together. The next one is really the same thing. If you have the sum of the difference of two sequences, you can apply the summation to each one of those separately, separated by a minus sign. Okay, the last one is probably the trickiest one, at least to see it right away. So it says, suppose n is a number that's bigger than j. N is some number bigger than j. And you are adding, let's actually put some numbers in here just to make it a little bit easier. So let's say you've got to do the sum from k equal 5 up to, let's say, 13 of just some sequence a sub k. Well, we really prefer our summations to start with 1. So what this is saying is you could say, okay, we're going to go ahead and add up from 1 up to 13. But this is too much. We've added too much here because we were only supposed to do from 5 to 13. So what we want to do is we want to get rid of the first part of the sequence. We want to get rid of from 1 up to 4. So we're going to subtract a sub k, where k starts at 1 but goes up to 4. This eliminates that first part of the sequence that was added up here, and it leaves just the sum from 5 up to 13. So this can be particularly helpful. You'll see an example in the problems below where we use that. Okay, more theorems. These are special summations. The first one here is just saying, suppose you're going to add up a constant. You're doing the summation of a constant. So maybe it's like the sum of 3, where k equals 1 up to 5. Well, what does that summation actually mean? It says to start plugging k in. Well, there's nowhere to plug k in. This is just a constant function, which means every time we plug k in, we just get 3 out. So we put k equal 1 in, we get 3. Put k equal 2 in, you get 3 again. Put k equal 3 in, you get 3 again. Put k equal 4 in, you get 3. Every single time you get 3 out, but you can only plug in 5 times. 1, 2, 3, 4, 5. So this sum really represents adding 3 5 times. In other words, it's 3 times 5, which is where you're getting this. It's the constant multiplied by the upper index. Now, the only way this works is if the k value starts at 1. We would have to modify it otherwise. Okay, so that's all the first term says, or the first formula. That one should be pretty obvious. The other ones are not obvious. Okay, so this next one, this is a famous one. It says that if you're going to add up all of the integers, the positive integers from 1 up to n, that is equal to n times n plus 1 over 2. Right? This sum represents the sum of all the positive integers less than or equal to n. We're going to prove this formula in just a second. The next one says if you need to add up all of the squares of the first n positive integers, it turns into this formula. And then the last one is the sum of the first n, the cubes of the first n integers is this formula here. So we're not going to bother with proving these. We will prove this one when you get to calculus, but we should have proven this formula last year. If not, we're going to do it again right here. So we want to prove the sum of the first n integers, n positive integers, is always equal to n times n plus 1 over 2. Okay, so to do this, we're going to call this thing s sub n just so I don't have to keep rewriting it. So this is saying the sum of the first n integers. So I'm going to rewrite that part out. The sum of the first n integers is 1 plus 2 plus 3 plus, all right, and then when you get to the end here, you're going to have n minus 1 plus n minus 2, sorry, just n, sorry. We're going up by 1 each time. So plus n. Now what we're going to do is we're going to rewrite the same exact thing, but we're going to write it in reverse order, which means if we went in reverse order, this would be n. The next one that we add would be 1 less than this, n minus 1. Then 1 less than this one, which would be n minus 2. And we keep doing that until we get all the way down to the end, which would be plus 2 plus 1. So I've written the exact same thing here. I've just written it in reverse order. Now what we're going to do is add straight down. So on the left-hand side, when I add those, we get 2 times s sub n. They're the same term, so you can just combine them. 2 times s sub n. Adding here, I get n plus 1. 1 plus n is n plus 1. If you add these two, again, you're going to get n plus 1. Adding these, again, gives you n plus 1. And every single time you add down, you're going to get the same sum. It's always going to be n plus 1. Adding these two, n plus 1. Adding the last two, still n plus 1. Okay, so how many n plus 1s do we actually have here? Well, they're already counted out for us. If you think of these as columns, there are n columns here. They're counted out right above, from 1 up to n. So there are n terms here. Well, another way to think of that is we're just doing this n times. So it's n times n plus 1. There are n of these there. And if I bring this over, let's move this all up. Our goal was to get the formula for s sub n, so I just need to get this by itself. We just need to divide over. So s sub n equals n times n plus 1, all divided by 2. And that is the formula that we wanted to prove. Right? Remember, we defined s sub n to be this thing, so we have just established that it is n times n plus 1 over 2. So again, just to make sure it's clear what we've proven here, suppose I ask you to add up the first 100 integers. So that would be the sum of k, where k goes from 1 up to 100. In other words, this is 1 plus 2 plus 3 plus 4 plus all the way up to 100. So if we apply that formula, it says to take n, which is 100, multiply it by n plus 1, which is 101, divide that by 2. Simplifying this would be, you could go ahead and divide the 100 by 2, so that's 50 times 101, which is 5,050. So the sum of all of these numbers adds up to 5,050. Okay, so let's try using some of these properties. In this first example, we can see that we have a constant times some sequence. So we can go ahead and just pull that 3 out. That's using that first property. This sum is the sum of just integers that starts at 1 and goes up to 5. So this means we get to use the formula, I'm just going to keep the 3 there in front, n times n plus 1 over 2. And in this case, the n is this number, so we're going to put 5 in each of those spots. So this is 3 times 5 times 6 over 2, which is going to be 45. So this summation should come out exactly to 45. Okay, the next one, we have a sum inside of the summation. So we can use the property that says the summation essentially distributes to each of those terms. So this is the sum of k cubed, k equal 1 up to 10, plus the sum k equal 1 up to 10 of just 1. Okay, if we look at this term here, we're adding up the cubes. So we can use the formula for the sum of cubes, which was n times n plus 1 over 2 all squared. Notice the inside of this is the formula for the sum of just the integers, but we square it at the end of it. So in this problem, though, we're going to be plugging in 10 in for the n on that. Let's go ahead and address this as well. This is of the form the sum of a constant. So the formula said it's just going to be the upper limit multiplied by that number. That's really just 10 times 1. This says you are adding 1 10 times. Starting from k equal 1 and just counting up, you add it 10 times. So 10 times 1 just gives us 10. All right, so plugging in the n on the first one, you get 10 times 11 over 2 all squared plus 10. Inside here, you're going to get 55 squared plus 10, and that comes out to a total of 3,035. So this entire sum is 3,035. Now, could you do this without using these shortcuts? Absolutely. You could write this out. You could completely expand it. So the first term would be 1 cubed plus 1. Then the second term, 2 cubed plus 1, plus 3 cubed plus 1. And you could just keep going until you get up to that last term, which would be 10 cubed plus 1. But I do think this would actually take longer to expand it out than to just apply these properties. And the other benefit of what we did here is all of this work is going to be the exact same. Even if we make it 100 terms, you're just going to plug 100 into these two spots and make that 100 here. So the overall simplification would not be much more work. Okay, next one. This has got 3 terms. So we're going to apply the summation to all 3 of them. For the second one, notice that it is a constant multiplied by k. So I'm going to go ahead and pull the constant out using that first property. And then the last one is the sum of 2k equal 1 up to 24. Okay, so now we just have to apply the formulas to each one. This one is the sum of the squares. It's the messiest of them. It starts off the same way as the other formula, n times n plus 1, but then it has a 2n plus 1, and it's not divided by just 2, but it's divided by 6. So we have to plug 24 in each of those n's. The next one is just the normal sum of the integers, so it's going to be n times n plus 1 over 2, and again 24 is going in each of the n's. And then this last one is the sum of a constant. We're adding 2 up 24 times, so that is just 2 times 24. Okay, so if we start plugging in, this first one is really 24 times 25 times This is going to be 48 plus 1, so 49 over 6. Next one is going to be -7 times 24 times 25 over 2, and then plus a 48. Okay, you could go to your calculator at this point, but the first term here, I believe, comes out as 4,900. This term comes out as minus 2,100. And the final term we already know is 48. So put all that together, you get a total sum of 28,848. So adding up those 24 terms gives you 2,848. All right, last example. It looks like it's easier than the other ones, and for the most part it is, except there is one big difference here. You have to be real careful with this. You need to watch it on every single problem. The starting k value is 6. Every other one that we did, starting value of k was 1. But on that last one, the starting k value is 6. So this is where we're going to use the trick of, we're going to start by going ahead and using the 1 up to 20. But we're going to subtract off the ones that we don't want. So which ones we don't want are from 1 up to 5. We don't want those first 5 terms. So now each of those sums have an index that starts at 1. So we can apply our formulas to them. The 4 can come out. That 4 could have come out at the very beginning before we even applied this trick. And now we just have two sum of squares. So we just have to put out the formulas for those. I'm not going to write them with n this time because the value of n is different for each of these. So we're just going to have to plug in. So that formula says you start with the n, which is this, so it would be 20, multiplied by one more than this, 21, multiplied by this doubled plus 1, which would be 41, and then divide that by 6. So I'm just plugging all of that into this formula here. Okay, then we do the same exact thing with this one, except now n is 5. So we start with 5, we multiply it by one more, we multiply it by 6, we double this and add 1 to it, so that's 11, and divide that by 6. Alright, multiplying this first part out comes out to 11,480. Second part is 220. And then combining those, you get 11,260. And that's it. Now, if you haven't already figured it out, your calculator does have the ability to do summations. I would strongly encourage you to practice doing this method, because in calculus we will need to do this and you won't have the calculator. In fact, we will change the problem so that the calculator couldn't even help you, and you'll need to understand this procedure. But just to show you that it does work on the calculator. Okay, so to find the summation, you go to Math, and then it is near the bottom. You see summation here, and you can even see the sigma notation. So let's choose that option. And then you'll get a template to type in. So you can choose what you want the index to be. It's actually easiest to probably use X as your index, but if you want to stick with the letters that are there, you can still use the alpha button to make the letters work. So the sum where k equals 6 up to 20, and then just put the expression in here, so 4 alpha k squared, and there you go. That should match what we had down below. You can see those two do match. So yes, that would make it a whole lot easier, but I do encourage you to try working them out by hand before you go straight to the calculator. All right, that completes this section of notes. Hopefully this is helpful. If you have any trouble with the homework, then let me know. Send me an email, and we'll see you guys in the next video.